In this video, I'll be showing you the solutions for Chapter 5, Thermochemistry. We're going to be looking at Hess's Law and heats of formation, Chapters 5.6 and 5.7, and again, this will be the solution to the worksheet. Okay. Problem number 1, it gives you two equations, 1 and 2, and it asks you to find the delta H for the third equation. Okay. The way you do a problem like this is you look at the equation that you want to solve for, and you're going to rearrange the top two equations, which you know the delta H reactions for these. So you're going to rearrange these so these two equations add up to the third equation. Okay, the first thing I'll look at is the phosphorus. I find the phosphorus in equation number 2, and I'm going to look for two things. I'm going to make sure it's on the right side of the equation. It's a reactant, and it's a reactant up here. So that I'm fine with that. The second thing is let's check the coefficient for the phosphorus, and it has a coefficient of 2. So that tells me that I don't have to do anything to this equation, and I don't have to do anything to the delta H. Everything's fine on that. The second thing I'll check is the chlorine. Okay, when I check for chlorine, I find that it's in number 2 and it's in number 1. Generally, I say if you find this in two different equations, I would just leave it alone. If you find the chlorine in the reactant or the product, either one, in more than one equation, then look for something else. And the next thing I'll go down to is a PCl5. Okay. I mean, I could actually solve this from here because I can see what's going to happen, but it won't always be so clear, and especially if you have three equations. But in this case, I'll just go to the PCl5. Okay, two things you want to make sure. You have PCl3 as a gas. This is PCl5 as a solid. So where I find it is in equation number 1 as a reactant. First of all, I want it to be a product, so what I can always do is, and I'll just rewrite this. I'll just rewrite it on top. I'm going to flip the equation. PCl3 as a gas, and the chlorine as a gas will produce PCl5. So what I did is I just flipped the equation. By flipping the equation, the delta H was a positive. By flipping it, I just make it a negative, 87.9 kJs. Okay, now I'm going to check the coefficient. It does not have the same coefficient, and I'll just point out, flipping it put the chlorine on the same side now, so it won't cancel out now, it'll add up. So, I could figure out that I need 5, so I know there's going to end up being a 2 there. But I'm going to do this off the PCl5. I see that I've seen this same coefficient at 2, so I can multiply this entire equation by 2, because that gets me the right side and the right coefficient for PCl5. And Hess's law is all about the law of conservation of energy, first law. And it's called the law, Hess's law of summation. So if I can add two equations to make a third equation, then the delta H's are going to add up. Now, if I multiplied this equation by 2, that means that my delta H doubles. Okay? And by doubling that, I get 2 times 87.9, say negative 175.8 kJs. Okay, and now I can just add up my delta H's, and it comes to negative 750. And I guess I rounded that off, but I guess if I do sig figs right, it should be 749.8 kJs. Know it to the 10th. Okay. You do have the answer given, so you know that you're right. And then the last thing I'd like to do is make sure that these two equations, everything adds up well. The 2p comes down. 2 chlorines plus 3 chlorines makes 5 chlorines. And the 2PCl5 is on the right hand side. Everything else cancels. So my 2PCl3s here cancel with this. And then my chlorine gas here, that got flipped. That's it. That's all that cancels, so we're good. Alright, and 2 plus 3 equals 5. Alright, and that's Hess's law. I'm going to flip over and do a heater formation problem. And I'll try and make this up. Okay. So I'm going to make sure it's centered. Okay. Heater formation. When it comes to heater formation, you're going to be giving a series of heats of formation. Now, if you're going out of the textbook, you want to look for Appendix C, and that's page 1041. You'll find all thermodynamic quantities listed, and one of these is the heat of formation. The heat of formation is how much, what's your energy change in forming any compound from its component elements. And if it's diatomic, it'll be made from the diatomic element. In standard state conditions, okay, that's what the little 0 means. That means that 1 atm at 25 degrees at a molarity of 1. These are your standard state conditions, okay? It all comes down to this equation, that you can find the heat of the reaction by totaling up all your delta H of your products minus the reactants. And one thing that's missing here is you want to multiply this by moles, by the number of moles from the reaction, okay? Now, I always tell students, whatever you do, write this equation down, because, you know, students will see an equation and they'll tend to take the reactants and subtract the products, but it's actually products minus reactants. Okay, so if I look at this, I want to multiply 4 times the delta HF of NO. Okay, then I'm going to sum it up with 6 waters. That'd be the delta HF of the water. Okay, these are your products. So I'm going to add all them up. Then I'm going to subtract the reactants. I have 4 times NH3, which is there. So I'll say the delta HF of NH3. And then I'm going to add that up to oxygen. It'll be the delta HF of oxygen times 5. Now, you don't find oxygen listed, and there's a reason for that. The delta HF of anything at standard state in its natural condition of an element is equal to 0. In other words, if you already have O2, it doesn't take any energy to make it O2 because it's already O2. So the heat of formation is 0 for anything that's elemental. So that's something that will always come up. But it does have to be in their correct state. At 25 degrees, oxygen's a gas. If that was a solid, if that was a liquid, then you would have a different HF. Okay. Now we're just going to throw the numbers in. Okay. So I got 4 times NO is 90, positive 90. And watch your signs on this. 0.37 kJs. All right. Moles of this cancels out with the moles of that. So your unit just turns into kJs. Okay. Plus 6 moles times water, negative 241.82. That'll be kJs. And this is your products. Now I'm going to subtract that times 4 times the NO, which is the NH3, the ammonia, which is negative 46.19, and that's kJs. And these are your reactants. So this is just very simple nature reaction. Now, if you want to just summarize it, 4 times 90.37, this number is positive 361.48. Then I'm going to add that up, and this number is going to be negative 6 times 241.82. So that number is going to be negative 1450.92. Total that up. And it totals up to a negative 1089.44. Okay, and then this is a negative, so it's a negative times a negative. It's going to end up being a positive. So here's the total of your reactants. 4 times 46.19 negative. So it's negative 184.76 kJs. And so negative 189.44. Negative times a negative is going to be a positive 184.76. And you just have to be careful and watch your signs to get this right. The delta H of the reaction will then be 904.68 kJs, and it's negative. And the sign, if you don't get the sign right, you're totally getting the problem wrong. Because if you flip this reaction and you took reactants minus products, if you flipped it, this will become a positive 904.68. So you have to have the sign correct to get the problem right. And that means you just have to make sure you're summing the delta H of the products minus the delta HF of the reactants. Excuse me. All right, flip to the bottom, to the back. I have another Hess's law problem. Just seeing if I'm on there. Okay. Calculate the heat of reaction for the formation of gaseous diborane. Now, before we were doing this at home, if I was doing this in class, I wouldn't give you the equation. I would just leave it blank, and I would let you write your own equation. Well, the heat of formation of gaseous diborane, that's B2H6, that's what we're forming. So if I was writing this, if I was generating this, synthesizing this, I would need 2 borons. So I would put 2 boron solids, that's what the standard state for boron. And hydrogen's going to come in H2 gas. Okay, it's diatomic. So elementally, hydrogen's considered to be H2, not just H. So to get 6, I need 3. So that's a heat of formation equation. 2 B's plus 3A2 makes B2H6. I'm forming this from its elements. The reason I even would do a problem like this is you can't practically just make diborane from its elements and figure out the delta HF of that. So what you would do is you would combust boron. You do a combustion reaction, calculate the delta H for that reaction. Then you combust hydrogen to make water. Easily you can find the delta H of that reaction, much more practical. Then you would actually burn the diborane. You'd combust the diborane to make B2A3 and H2O. So from these 3 reactions, I can generate this 4th reaction. Okay? And so it's a little more complicated. We have 3 reactions. I'm going to follow the same steps. And this is interesting because I'm going to start. Now, I never start up here. So there's people and teachers who will teach from the reactions, and I don't like to do that. I like to go from my goal down here. I want 2 boranes, and I find boron here, but it has a 4. So what I'm going to do is multiply it by 1/2. Okay, and if I multiply this by 1/2, I'm going to multiply my delta H by 1/2. That's the law of conservation of energy. Okay, law of conservation of mass. Okay, distribute out the 1/2, I get 2, 3/2, and I get 1. Okay, and I don't rewrite this. Okay, I would just write them there, cross it off. It keeps it simple. If you try writing this equation, you're just going to make it very ugly and complicated. 3 hydrogens. Here's the only place I find hydrogen in number 2. Well, how do I turn a 2 into a 3? If I looked at it like a dimensional analysis problem, I'd say, well, divide by 2 and multiply by 3. 2 times 3/2 equals 3. So I'm going to multiply this equation by 3/2. Okay, distribute the 3/2. 3/2 times 2 gives me 3. I get 3/2 oxygen, and then I just get 3 waters. And again, I take my delta H and multiply it by 3/2. Let's grab these numbers real quick. 2509.1 divided by 2 gets me negative 1254, and I'll say 0.6. Okay, and 571.7 times 3 divided by 2 gets me negative 857. I'll go with 0.6. Okay. The last problem, I've done the hydrogen now. Now I look for my diboron. I only find it here. Right coefficient, but the wrong side. So I'm going to just rewrite, strike out this equation. Now I'll just strike out the equation and I'll rewrite it. The B2O3 comes on the left side. The 3 waters come on the left side. And on the right side, we get the diborane where we wanted it. And we get 3 oxygens. For flipping it, all we really have to do is change the sign. Positive 12, 21, 47.5. Now Hess's law tells me these 3 reactions add up, your delta H's add up. So we're going to use summation negative 1254.6 minus 857.6 plus 2147.5. That didn't work. $1254.6 negative minus 857.6 and then plus 2147.5. So I get 35.3 positive. With the rounding of the fractions, I had 35.4, and that's close enough. You're always allowed to be plus or minus. Your last digit is always estimated. So 35.4 is acceptable, 35.2 would be acceptable. All right, and I'll just check to see that everything cancels out. The hydrogen, the boron came down, the hydrogen came down, and the diborane came down. Everything else cancels out. So my B2O3 over here cancels out with B23 over there. My 3 waters here cancels out with my 3 waters there. And an oxygen, 3/2 plus 3/2 makes 3 oxygens. And that cancels out with those 3 oxygens. So the world is good. That's Hess's law of summation. Okay. Another heater formation problem. Again, I always write out this equation. And it's going to be, you have these. If you were doing this out of your textbook, you would be looking it up on page 1041 and Appendix C. That's in Brown LeMay's chemistry book. Products. I got 2 times FeCl3, so that's 2 times negative 400. And that'll just become kJs. I will sum that up with 3 waters. So here's water, 3 times negative 241.82. And then these are all my products. Sum them up. Minus my reactants. Okay, so I got F2O3. So it's negative 822.16 kJs. And then I'm going to add that up with 6 HCl's. So 6 times 92.3 kJs. Okay, so what I get is I get negative 800 plus a negative 725.46. So my total of the products is negative 1525.46 kJs. Then I'm going to subtract that from the 92 is negative. So I got negative 822.16 plus that's negative 553.8. Sum those up. I'm getting now minus a negative becomes a positive, so it becomes 1375.96. And I find out that the delta H of the reaction from heats of summation is negative 149.5 kJs. And there's your answer. So that's Hess's law and summation of heat of formations. In both, what we're doing is we're finding heat of reactions. All right, go to the next section.